some examples of famous partial differential equations. Let us first look at wave equations. Here is an example of a wave equation in 3D, where we have where the space variable is in 3 dimensions. So we have the x coordinate, y coordinate, and z coordinate. The equation is u tt, which is second derivative of u with respect to t, equals c squared, which is a constant, times the second partial derivatives of u with respect to x plus the second order derivative of u with respect to y plus the second order partial derivative of u with respect to z. So it's a sum of second order partial derivatives of u with respect to each space coordinate. This is a shorthand notation for this sum of second order derivatives, which is this upside down triangle square, which is like gradient square u, right? So some other people also write this gradient square u as a triangle, which reads Laplace or Laplacian u. So if we have a 2D wave equation where we have two space coordinates, say x and y, then this gradient square u will be equal to partial u partial x squared plus partial u partial y squared, right? And if we're in the one-dimensional case where we have only one space coordinate, meaning x, then this expression is exactly uxx, right? So this is an expression of the 1D wave equation. Why we are calling these equations wave equations? The short answer is the solution permits or exhibits wave-like behaviors. Here is an example of a wave propagating along a string where both ends are tied and fixed. Maybe you have played with this kind of rope before. If one wiggles the rope here, then the wave starts to travel down the rope until it reaches the other end, and then it flips around and travels back. Okay. And here is an example of a wave in two-dimensional space. In the surface of water, for example, if you throw a pebble or a stone to the center of a pond, you may observe this wave-like behavior on the surface of the water. The wave sort of propagates outwards from the center, which is the landing location of the stone, where the wiggle is initiated. One thing to note that is when you look at these waves from these animations, it may be deceiving that the particles are moving like this or like this, like they are traveling along this direction, and then upon reflection it travels back. This is not the case. Rather, the rope is going up and down, right? The rope at each location x is actually going up and down. So in this example, x represents the location, u of x at time t represents the vertical displacement of the rope at the particular position x. Take the wave in the water pond as another example. When you look at this wave, it seems that the particles are moving in this direction. In fact, the water droplets from this position are not traveling themselves all the way here. Rather, the movement is in the vertical direction. The movement between neighboring water droplets are coupled, so the vertical vibration of the water droplets in the center will cause water droplets to move up and down, and And the vibration of these droplets will further cause other droplets to move up and down, and hence the vibration or the up and down movement propagates. It is the same as in the previous example. It is not like that this piece of rope is traveling, rather the rope is going up and down at all locations. In this example, in X and Y represents the position coordinate in the pond, and U, X, Y at time t represents the vertical displacement of the particles at location X, Y at some fixed time t. And here is a solution of 2D wave equation, where you see these oscillatory wave-like behaviors. Here we have the boundary condition specified as 0. In other words, the wave is not wiggling along the boundary. Imagine you can observe this kind of behavior where you hold a square sheet and initiate some wave, but then fix all four sides and corners. In the examples here, oscillations or vibrations are perpendicular to the direction of the wave's advance. It is called transverse waves in physics. This is in contrast to a longitudinal wave which travels in the direction of its oscillations. One example of such longitudinal waves is the sound wave, which we'll talk about later. Here, in front of us is the so-called wave equation that describes all kinds of wave-like behaviors, and many other physical laws are also expressed in the form of partial differential equations. And in particular, waves are very important in optics, fluid mechanics, sound propagation, and so on. So this is a very important and fundamental partial differential equation. Speaking of sound propagation, here is maybe one of the most familiar example for you may have. So here is an example of a tuning fork. If you make this fork vibrate, it will send the sound waves. The waves are pressure waves. The cartoon here show lines of crest. In some areas, many crest lines are joined together. You can imagine the air pressure here is high. In some other areas, the crest lines are not so dense. You can imagine the air pressure is relatively low here. Intuitively, the vibration causes differences in air pressure across the space coordinates. This is what eventually vibrates the membrane in your ear, and this is why this is what lets you hear what I say if we're sitting in the same room. Of course, now there's a bunch of electronics between you and me, so more things are happening for my voice to reach you at the moment. Here, the movement of the air particles caused by the vibration is parallel to the direction of the wave, which, by the way, results in regions of high pressure and regions of low pressure. Here, as mentioned earlier, the sound wave is an example of the so-called longitudinal wave because of the parallel directions of between the direction of the wave's advance and the direction which the air particles vibrates. Our purpose here is not to derive this equation from physics, but illustrating the idea that the wave equation models all kinds of waves. Here is an example of sound wave, and we have seen a wave in the surface of water in the previous slides. And also you can model light waves and so on and so forth. So this is pretty amazing. One side note here is that for example, for the 1D wave equation, the the sinusoidal equations possible solutions for the wave equations. If you just think about it or verify yourself, you can see that the cosine x minus ct is actually a solution of this equation. In other words, it satisfies this equation. So we know the cosine, the derivative of cosine is sine, is minus sine, and then the derivative of sine is cosine. So and then taking into account the sign changes, you can verify that this actually satisfies this equation. And if we have sine of x minus t, if you sit down and verify that, you can see it is also a possible solution of this wave equation. So, and we'll come back to this topic later, that we need boundary conditions to actually guarantee a unique solution for the wave equation and other partial differential equations as well. There are imaging techniques in practice that allow you to visualize sound waves. So here is an example. Of course, it has to be done with fast cameras and ways of having contrast of air around. And here is a frame of a video of a person clapping. If you pay attention, you can see the wave propagating through the air, and you can watch the full video in YouTube by searching these titles. And here we just show you a frame, and you can see the crest of wave after the person has clapped, and you can also see the differences in the air pressure. And here we highlight the crest line, one crest line here. By the way, the crest of a wave is the maximum value of upward displacement within a cycle. So there are many applications of modeling waves, and in biomedical engineering, one classical application of this kind of modeling technique is the use of ultrasound, which allows imaging of inside human body, right? And the University of Virginia, there's a focused ultrasound group. They developed technology that is possible to focus ultrasound to achieve maximum energy at a certain point, and so cause different effects such as microbubbles, burst of microbubbles. So they can be potentially harnessed to improve drug delivery as an example. And here are some links that you can read to learn more about this focused ultrasound technology and the possible applications. So obviously we would like to design these waves, and correct modeling and simulation is a primary part of the process. And in the next lecture, we're going to learn how to numerically solve partial differential equations. And the second equation we would like to give or introduce is the so-called heat equation or diffusion equation. Heat will flow from hotter bodies to adjacent colder bodies, as you have learned from physics. And in fact, this equation more generally models the diffusion process, such as a drop of ink in a bucket of water, and the ink flows from high concentration areas to no concentration areas. So it does not only model the heat conduction, it can model more general diffusion processes. So here is the heat equation in 1D. We have the ut, the derivative with respect to time, is equal to a d squared, which is a constant, times the second derivative with respect to space. And d squared is usually called the diffusion constant. So let us take the heat distribution rod as an example. At a high level, the heat equation is saying that the rate of change of a temperature is proportional to the curvature of the temperature function. So the curvature is of a function is the second derivative of a function, right? So intuitively, the curvature describes the difference of nearby temperatures at each location. So so this equation says that the temperature tends to change more quickly at points where the temperature graph curves, and it changes in the direction of the curvature, as shown here. And as a result, the temperature at a point will tend to approach the average of nearby points, the average of the temperatures of nearby points. So you get the gist of it, and we're not going to go deeper into the background of heat equation here, but instead we'll post a video for you to watch later from 3 Blue 1 Brown that gives wonderful illustration of the physics and intuition of the heat equation, and hopefully gives you better interpretation of the heat equation and partial differential equation in general. And the video will be posted also in the course website. So here we also present the multidimensional form of heat equation, where ut is equal to d squared times the gradient square u, or Laplacian u. We have seen this expression, the gradient or upside down triangle square u, in wave equation, and you can see that this equation is looks very similar to the wave equation, and the difference is that in the wave equation we have the second derivative utt instead of ut here, as in the heat equation, right? So here is an animated plot of the evolution of temperature in a square metal plate, which is taken from Wikipedia. So, and the height and the redness indicate the temperature at each point. The initial state is as specified here, which has a uniform hot hoof-shaped region, the red region, and surrounded by a uniform cold region, which is the yellow region. So here is the initial condition, and we can see the diffusion process. As time passes, the heat diffuses into the cold region. Example of 1D wave equations. There are many possible solutions that satisfy that equation, like the cosine x minus ct equals sine of x minus ct. So without specifying boundary conditions, the solution is not usually uniquely defined. So we have, in general, an equation that involves a function and its partial derivatives, and we also have a domain of interest. And this domain can be finite or infinite. So we need to specify the values on the boundary of the domain so that some kind of values on the boundary of the domain so that we may have a unique solution of the partial differential equation. And in general, here are two common types of boundary conditions. One type is the so-called Dirichlet boundary condition, and the other one is called Neumann boundary condition. In the case of Dirichlet boundary condition, it is the conditions are specified in the ways of the values of the functions. For example, in this squared domain, if we have a Dirichlet boundary condition, we may specify values on each of these four sides. So, for example, we may say ux naught y t is equal to f of y for some function f, right? And on this side, we may say y naught is fixed. The x can vary, so we may say ux y naught t is equal to g of x, for example. So if we specify Neumann type of boundary conditions, one specify the value of derivatives on the boundaries. As an example, one may say the partial u, partial y, for example, on this point on the boundary is equal to some value. And one can also say, okay, the sum of partial derivative with respect to x plus some partial derivative with respect to y at the point on this boundary is equal to some value. And so if we just specify derivative values on the boundary, we are specifying the Neumann type of boundary conditions. Of course, there are mixed boundary conditions where you specify both the values and the derivative values, which are usually called the Robin conditions, which are more complicated. And in this course, we're just going to talk about these two type of boundary conditions. Now let us look at the heat equation as an example. So we're looking at the heat distribution on thin rod. The heat equation is, if we recall, as follows: ut equals to d squared times uxx. We have a time variable here, so in principle, we need some initial condition. So here we have ux at time 0 equals f of x for some, so we have some initial distribution f. So we would like to say that for different physical assumptions or processes, we may have to impose different boundary conditions. For example, if we assume that both ends of the thin rod are immersed in ice water, we know that ice water has temperature 0 degrees Celsius, right? So an appropriate boundary condition would be u at x equal to 0 for all time t is equal to 0, and u at x equal to L for all time t is equal to 0. In another situation, if somehow there is no heat exchange between the rod and its environment, here are the more appropriate boundary condition to impose. We have partial u partial x at 0 for all time t equals 0, and partial u partial x at x equals L for all time t equals 0. Of course, we're waving our hands a little bit and have not explained why exactly this situation corresponds to these boundary conditions. But you can, of course, search on the web to learn a little bit more physics behind this math. But the idea is that for different situations and different physical processes, we need different boundary conditions. And in fact, specifying the correct boundary condition that guarantees a unique solution and solving them with the correct boundary condition are the key parts of the solution of partial differential equations. And here is a summary of what we have introduced so far. We have learned the definitions of partial differential equations and compared these with the definitions of ordinary differential equations. And we have classified second-order differential equations, partial differential equations into elliptic type, parabolic type, and hyperbolic type. We have also introduced some fundamental and famous partial differential equations such as heat equation and the wave equation, and provided some physical intuition of them. We have also learned some common types of boundary condition that were imposed on certain domain for partial differential equations. I'll end this lecture with a quote, and hopefully you agree and are more convinced of this, since this is a quote by Stephen Strogatz. Since Newton, mankind has come to realize that the laws of physics are always expressed in the language of differential equations. So in the next series of partial differential equations, we'll learn how to solve them numerically, and in particular with finite difference method. And thank you for your attention, and see you soon.